Howdy, everybody. Hope you're doing well whenever you are. We're here for day 11 of Advent Code 2016. Yeah, days have been going okay. Probably overanalyzed last time, trying to fix and change things, but sometimes you're just having fun for certain definitions of fun, I guess. But I've really enjoyed the stuff. Love all your comments. So please keep them coming. They help me learn more things and figure stuff out and just know things in general about how to solve problems and stuff. Something I'm interested in doing, so I plan to keep doing it. So with that, let's just try and solve this one. See if we can't learn something from it. So it is radioisotope thermoelectric generators. Global thermonuclear. That's a different thing anyway. You come upon a column of 4 floors that have been entirely sealed off from the rest of the building except for a small dedicated lobby. There are some radiation warnings and a big sign which reads Radioisotope Testing Facility. According to the project status board, this facility is currently being used to experiment with radioisotope thermoelectric generators, RTGs, or simply generators, that are designed to be paired with specifically constructed microchips. Basically, an RTG is a highly radioactive rock that generates electricity through heat. The experimental RTGs have poor radiation containment, so they're dangerously radioactive. The chips are prototypes and don't have normal radiation shielding, but they do have the ability to generate an electromagnetic radiation shield when powered. Okay. Unfortunately, they can only be powered by their corresponding RTG. An RTG powering a microchip is still dangerous to other microchips. I guess presumably unless they're powered as well. In other words, if a chip is ever left in the same area as another RTG and it's not connected to its own RTG, the chip will be fried. Okay. Therefore, it is assumed you will follow procedure and keep the chips connected to their corresponding RTG when they're in the same room and away from other RTGs, otherwise. These microchips sound very interesting and useful to your current activities, and you'll likely try to you'd like to try to retrieve them. The 4th floor on the facility has an assembling machine which can make a self-contained shield computer for you to take with you. That is, if you can bring it all of the RTGs and microchips. Okay, so we're trying to get to the 4th floor then. Within the radiation shielded part of the facility, in which it's safe to have these pre-assembled RTGs, there is an elevator that can move between the 4 floors. Its capacity rating means it can carry at most yourself and 2 RTGs or microchips in any combination. They're rigged to some heavy diagnostic equipment. The assembling machine will detach it for you. As a security measure, the elevator will only function if it contains at least 1 RTG or microchip. The elevator always stops on each floor to recharge, and this takes long enough that the items within it and the items on that floor can irradiate each other. Okay? You can prevent this if a microchip and its generator end up on the same floor in this way, as they can be connected while the elevator is recharging. You make some notes of the locations of each component of interest. Your puzzle input. Before you don a hazmat suit and start moving things around, you'd like to have an idea of what you need to do. When you enter the containment area, you and the elevator start at the 1st floor. For example, suppose the isolated area has the following arrangement. The 1st floor contains a hydrogen-compatible microchip and a lithium-compatible microchip. The 2nd floor contains a hydrogen generator. The 3rd floor contains a lithium generator. As a diagram, the initial state looks like this. So here's the floors. This is the elevator. HG, this is the generate. These are the generators. These are the microchips. Then to get everything up to the assembling machine on the 4th floor, the following steps could be taken. Bring HM to the 2nd floor, which is safe because it gets powered from the hydrogen generator. So you move this up. That's fine. Bring both hydrogen items to the 3rd floor. That's still safe. So there's a generator here, but everything, all the microchips are powered. So, okay. Leave the generator on floor 3. Bring the hydrogen compatible chip down. Yeah, you probably bring it down to bring LM, and then you bring them both up. Yeah. Now you bring these 2 up. Then you'd like bring like one of them down, and then 2 of them up, and then one of them down, 2 of them up. Yeah. Okay. So you just have to move them one at a time, and you have to make sure that when you move them, you haven't like left a microchip unguarded by its generator if there's other generators around. Okay. In this arrangement, it takes 11 steps to collect all of the objects at the 4th floor for assembly. Each elevator stop counts as 1 step, even if nothing is added to or removed from it. In your situation, what is the minimum number of steps required to bring all of the objects to the 4th floor? Here is your puzzle input. This is a crazy puzzle input. It's like parsing sentences. We'll have to think about that. But okay. So what's going through my mind here? What are these called? Like we've done these before, like state graphs. So we just generate potential next states, determine which of the states are valid. Like so we want to find like our neighbor function essentially, or our successor function. We want to say which ones are valid of the next possible states. That is to say, like if we're in this position, the elevator's here, so the only 2 that can move are these 2. So a possible state is to move this one up, or this one down, or this one up, or this one down, or both of them up, or both of them down. Like those are all of the potential states, but some of those are not valid, right? This one you can't move up. That does you no good. Or sorry, it fries the chip, so that's invalid, right? We'll have to track visited. This is, we're just going to do a BFS, right? Like sometimes I get asked what is the difference between like a BFS and a like Dijkstra's algorithm. I mean, Dijkstra's algorithm, where all the weights are 1, is essentially a BFS search. I think I've talked about this before in the channel. The reason being is like if you add everything to the priority queue, but they all have an equal priority of 1, then like you're basically doing them in order. I don't think there's a better way to do that. The reason why you do a BFS, by the way, and not like a DFS, for example, in previous days we've done DFSs, which is depth first search, meaning you're like trying to dig down to a specific part of the tree. The reason why you do that is because, or you do it that way, is because you want to be able to do like some pruning and be able to say, oh, this is a bad way, so I can skip these ways, and then that helps you like find good paths, if that makes sense, quicker. A BFS is where you're like, in this case, you're saying like, oh, all things are equal, potentially equal, so I'm just going to pick all the potential, I'm going to take all the potentially equal ones in this like quote unquote row of the tree and try them in order, see if I get to the end. And then if you ever get, and so just think of it, you're like trying it this way and this way and this way. And then if you like ever get to the end, you know that you found the fastest way. I just realized that's what it's asking, right? Yeah, the minimum number of steps. You know you've got to the fastest because you've always been scanning like, okay, at 11 steps, here's all the possible states. At 12 steps, here's all the possible states. And so whenever you find one that is like quote unquote done, then you know that you found the minimum number. So it's still that's essentially, if you think about it, that's how Dijkstra's works. It's always picking the minimum. In this case, all of the states, all of the next states are minimums, because and so they would go on the end of the list, so that once you've handled all the states that are like one step above, you will work on the next set of them. So the question is, how big is this state graph? There is promethium, cobalt, curium, ruthenium, plutonium. So 1, 2, 3, 4, 5. Yeah, I think that'll be okay. Like the first time when, so like you just want to kind of think about how explosive the state tree is. Like if you have the ability to create a million new states, then it's going to be really slow, right? And so you may want to start thinking about, is there something I can do? So for example, this one might be a candidate for an A-star algorithm. And you say, for example, like you can ask yourself, how far are you from how far are each of the elements from being up here? And you like prefer to try those first. I don't think that will work. Because you could have like global min, or you could have local mins and maxes that like lead you astray. So I do think you just have to do a BFS. I'll have to think about that. This may be one where someone says, oh, you can actually do an A-star instead of a BFS to solve it faster. Okay, so what do we need to do then if we know we're doing a BFS? The BFS itself isn't too hard. The general algorithm for a BFS is keep track of where you visited, keep track of your like to-do list, which in our case is just like a vec deck. We're going to pull from the top, or pop from the top and push to the back, pop front, push back. So you need those two things, and you're going to put your initial state on there first, and then we're going to just like, we're just going to pop from the top, and for each of them, we're going to say, what are my neighbors? Well, first we'll say, is it solved? And then we'll say, what are my neighbors? And then we'll add all the valid neighbors to the list, as well as add them to the visited list, right? Okay, so we do that. We'll have to parse this. I guess in each line I can just look for generator and microchip, and then like the one before it tells us what it is, except for these ones are dash compatible, which is a little weird. So yeah, generator. So I just look for those and like each one before it. Ooh, I could split do windows of 2. And if it has generator, then the first one is 1. So I filter by those to get the generators and things. I should probably have an enum for generators and microchips. And then what? I just use their strings. Interesting. I actually just need to know. All of them must have a pair. Otherwise, you couldn't move the microchip without, having a generator. So all of them have a pair, I presume. So you could actually treat them as a tuple, and you just need to know what floor they are on the tuple. So you'd be like, the first floor, you'd find promethium, and that would be 0 because you haven't seen it before or whatever. Then cobalt, and then you could do it in tuples. Yeah, how do we keep track of our state? Obviously, we need to know what floor the elevator's on, and then we need to know what each of them are on each floor. I mean, we could just use their names. That's easy enough. So we'd have a generator called promethium and a microchip called promethium. And then so we have an enum that's of type microchip, or an enum that has a microchip type and a generator type. And it tells you what floor, or no, it tells you what the name is, the element. And then how do you move? Like, that's what I'm thinking about right now. Like, do we treat each floor as like a vector, and we just like say, okay, move floor 2 has HG, we move HG up here and then test if it's valid. So you like add, you remove it from F2, add it to F3. You could also, like, again, like, I'm trying to think of how you would do this. If we have like a hash map of them or something like that, where we've tracked them and we know where each of them are on each floor. So we have a M and a G. And so let's say we have a hydrogen one, and it is like floor 1 and floor 2. So it's 1, 2. And the question is, and then L would be 1, 3. So then could you ask questions about that? Are all of them 4? Yeah. What do we need to do to determine if it's valid? If there's a generator on one, move it up or down. If there's a generator on one, all other microchips need to have an associated generator. So we can probably ask those questions with like some sort of iter tool. It's the parsing of this part that boggles me a little bit. You probably just keep a list of, like, you while you're parsing this, we have probably just have to keep a hash map of like this name and what index it is in the vector, and then we can move it over. So we could use ints that way. Yeah. I don't know if there's a best way to do it, so maybe I should just do it however I want, and we'll see. What is part 2, do you think? Should I worry about that? No, I probably shouldn't. Okay. Let's try and do this. Okay. Well, we're immediately stuck to parsing. I like the idea of just like doing tuples over each line and then putting them in the right place. So I do think I'm going to do a vec of like what floor are each of them on. Okay. So is that our only state? Oh, what floor the elevator is. So should we have a we should return the initial state then, right? So we say like struct state elevator usize equipment vec usize usize. So again, this pair is going to be the generator and the element. Or the microchip, I guess. Sorry, the microchip and the generator. So what leads me to almost want to do this, because then you can, well, we'll try it. We'll see what happens. I don't know. Is this very rusty? I was just thinking, is this Rust-like? I don't know. How else would you store them? You could store them in like a hash map by name and type. Like if you had an enum type, you could do that. No, okay. We're gonna do it like this. So then this is actually just going to return the initial state. So how does that look? We know the elevator is on floor 1. We need to keep a hash map. So let names equal fx hash map default, and it's going to be like an fx hash map of stir usize. We'll say let equal 0. So now for each row, so we're going to do input lines for each. And what are we going to do? We're going to do L dot split white space dot tuple windows dot so we only want them where B equals generator or B equals microchip chip. So that's going to give me the B will be this and means the A will be that. Oh, I'm going to do this though. There's commas and periods. So we'll do map the chunk c dot trim and matches a dot and trim in matches a comma. Okay. So we only want them that are generators and microchips, and then we'll do for each name type. We want to if we haven't seen it before, so if not names dot key, I guess we can do match names dot get name. Some I. We know we already have it. So we need to keep track of results. Let equipment equal so if we know we already have it, we've already added it, so it's already in the vector, and so we just want to match on type, and if it's a generator, we put it in, we'll do equipment I dot 1, so generator will be 1, is equal to the floor that we're on. So I need to enumerate this. Is equal to floor plus 1. If it's a microchip, it would be I just saw that I missed the name could have the dash compatible. What doesn't like about this? What doesn't like about I? Do I have to do this? So this is like the none case. I will still need to do this part, but it will be cur now right here. So I need to do this because we're going to add some stuff. Because after this, we'll want to do cur plus equals 1. And then we need to, oops. We need to add names dot insert name dot trim in matches compatible. Okay, so now we're going to return state elevator is on floor 1. The and then equipment like that. So the equipment is going to be a vec of U size. Is that what it doesn't like? Yeah. This. Oh, we want to insert this name with cur. So one thing is the vect is empty on the none types. So we need to is there like a grow or oh, I can just push it because it's a new one, right? Yeah. So I do equipment dot push. And what am I going to push? For this one, it's 0 floor plus 1. And this one, it is 0 floor, or no, floor plus 1 0. And then this is just equipment dot lane. So I actually don't need a track cur. Lane is 1, but index is 1. Oh, lane minus 1. Like that. I actually don't know what they look like now, but I mean, we can try and print it. So if we do derive, debug, sure. And then we print line. I just want to make sure that it's correct. Elevators on floor 1. We have a 1 1 3 2 3 2 3 2 3 2. Is that really what it is? That would be hilarious. Okay. Generator. Microchip. It is, yeah. So I think it's parsing it correct. Okay. So like you can see over here, this is our state, right? So we have the elevator, floor, and where each of the equipment's items are. So now we need to be able to ask ourselves some questions on this thing right here. So if we, I guess we're done with this. We can impl state. And the first question we have to ask is it valid? So we want to know each floor where there's a generator. So get the floors that have a generator. So what is that going to be? Self.equipment dot iter dot map generator g dot sorted dot unique dot collect. Oh, I want to do let floors equal this. So, and then we'll say like for floor in floors, if self dot equipment, we may not have to do this, we'll see. So we do self dot equipment dot iter dot filter. We only want to check the thing that's on the floor. Oh, it's any. So we'll do any where the chip and the generator where the chip, I think we can do this like this. It'll be, oops, floors dot contains chip and the generator does not equal chip. Like that. Gotta spell right, I guess. So is that right? Get the floors that have a generator and then go through all of them and oh, it's not any, right? So if we find any that have a chip on a floor with a generator and this generator is not on that chip's floor, so generator does not equal chip, we're in bad shape. So I think it is not. Because if I find none of these, it returns false. And we want to return none of these. So that's valid. Okay. So now how do we find our neighbors? Okay. So FN, I guess we can call them successors. That's what they use in the thing. I like neighbors. Who cares? So it's going to be self, and we're going to return a vec of state. So the things we need to do is go up or down on elevator. And then move 1 or 2 on the current floor. check if valid. So we can say like for elevator in what floor should we make the 0th floor? I mean, it really doesn't matter. We can say the elevator starts on floor 0 and goes up, and so that would mean this, 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 this. So if it's greater than 3 or equal to 0, then we continue. Is that right? Something like that. Okay. Okay, so if we ever go... No, we can go down if elevator ever equals self dot elevator. So we can go to 0, but we can't go to ourselves, and we can't go above 3. So we skip those. If elevator equals self elevator, that handles this saturating sub 1 if we're on floor 0. You don't go over. Okay. Go up or down on the elevator. Move 1 or 2 to the current floor. So we want to find all the equipment that are on this floor. I guess we do it by ID. Yeah, this is the part where it'd almost be easier to do it the other way. Because, like, how do I know? Well, I can easily tell which one are on the floor. But how do I know it's the first one or the second one, right? That it almost makes me want to change it up. we're really close. Once we get the successors, I realize we've been going on for a long time just thinking and talking about this, but we're really close because once we get the successors, we've now parsed the input. Once we get the successors, we should be able to relatively easily just do the BFS, and presumably the answer is like bloop shows up. Because what I wanted to do here was say, oh, just tell me, do I have a generator, or give me all the things that are on this floor, and I'll just, I'll do each of them by themselves, and then I'll do a combination too, and then for each of those I do the move. Let's see. I could just get a count of them, of how many there are, and then if I get a count of them, like say there's 5, then I could filter, if I say it's the 4th one or the 3rd one or whatever. Self equipment enumerate, flat map. I really just want to know which floor it is. Oh, well, I will know the floor, but I want to know if it's with which of the equipment or which of the elements, and whether it's a generator or a chip. So we'll flat map it. Chip, generator, and what do we do here? We'll say that's not even this, it's this. We can filter first. Does this even help? I don't think so. I was going to say, because I think I can just return an empty array for some of them, right? So we can say let this, then we can say if chip equal self.elevator, our current elevator, v.push I true, like it true being it's the chip. Let me say if generator equals self.elevator evelator. So close. v.push I false. V. We're missing one of those. So we're going to flat map those. We're going to have a bunch of i's of trues and falses. Dot collect. It's going to be a vec of usides bool. I fear I've made this harder than it should be. Okay. So now we have all the ones that are on our current floor, and now we're going to push them. Oh, I actually can do this outside. Right? And then for each going up or down, I can move them, right? So I can say how do I want to do this? Let's just start with each of the single ones. So we'll say on this floor dot iter dot for each. So we're going to get the floor and the is chip. And we're going to say let new new state equal state dot clone or self dot clone, right? And you make this clonable. And then we'll say if is chip new state. Oh wait, what did I push here? This is my current floor. I'm going to change that one. So if is chip new state dot equipment floor dot 0 equals elevator. I guess this is like a new floor. Else it's this one. And then we say if new state valid, successors dot push new state. So that's for the single ones. But we only do this, so we only do it if there's at least two. So if on this floor.lane is less than 2, continue. Otherwise, what we're going to do is do on this floor dot iter dot combinations 2. So we're going to pick 2 of them and move them. And we're going to do this similar for each. But we're going to get 2 of them. Is there like a combinations tuple? Tuple combinations? Because then I think I can do like this. Is chip 1, floor 1, floor 1. Is chip 2, floor 2, floor 2. Like that. Is this? Tuple combinations. 1, 2, 1, 3, 1, 4, 2, 4. Oh, 2, 2. Like that. Use a unary tuple. Oh, it's gonna return it like this. Huh. No? Closer expected to take 1 argument, but it takes 2. Yeah, that's what I was thinking. And I can't do this, maybe? Oh, I can. Okay, I must have had something in the way. Okay, I think those are all my successors. So let's just go over them again. I'm going to try and go up or down the elevator. And then I'm going to try moving each of the ones that are on this floor. Right? And so if it's and then I'm going to try moving each of those up and then each of those down. And then if I have enough to make combinations, I'm going to do up and down. Now I have my successors. Okay, that's a lot of work. So let's, does it still prints them. So let's do the thing. So let visited equal fx hash set default, and it's going to be a fx hash set of state. And let me say let frontier equal vecdec new. It's going to be fx. No, it's going to just be a state. I actually don't think I can do this. Okay. So we'll do while let some state distance, or sorry, count, whatever, equals frontier dot pushback. No, pop front. Okay. So we need to add our initial state to the visited and frontier. These both have to be mutable. Okay, so visited dot insert input visited, no, frontier dot pushback input 0, like that. This is clonable, I think, right? Input is a state. Okay, it doesn't like me to do that. But I can dereference here, I think. We need a state and a usize. Why doesn't this work? Can I do copy? I don't think vecs are allowed to copy. So I actually need to like this. Okay. So, oh, I need one more function. One more. So it's done where it is self.valid, and I guess I don't have to check this because it will have already known it's valid. But we're done when self dot, oh, well, it would be valid anyway. Self dot iter dot all sorry, a self.equipment .iter all chip generator chip equals 3 and generator equals 3. Okay. So we say if state.done return count, else for neighbor, or what are we calling it, successors? So we know they're all valid. We want them not to be on the visited list. So it's like if successor, no, it'd be like if not visited dot insert state, no, successor, frontier dot push back successor count +1, like that. Visited, I think that's right. Gotta clone all that stuff. 0. It's falling through here. Oh, I think it's just this. Nope. What does insert do? If it's already seen it, it returns false. Yeah, so I only want to do it if this is returned true. I only want to push back my successor clone count +1. Okay. Remember when I said we were almost done? Oh, I don't move the elevator up. Okay. So right here we have our new floors. State.clone new state.elevator is equal to new floor. We're gonna do that here too. 33. It's the magic number. How do I go from this one to this one? Oh, this is all the 32s. I actually think this is probably it. I hope. I really hope. That is the right answer. Okay. It took us a while to get there. Mostly because we were just trying to figure out what the heck we were doing. Let's go on to part 2. You step into the clean room, separating the lobby from the isolated area, and put on a hazmat suit. Upon entering, The isolated containment area, however, you notice extra parts on the first floor. Okay, I don't think that's going to be a big issue. So we just have 2 more parts that are on the first floor. These work just like the other generators and microchips. You'll have to get them up to assembly as well. What is the minimum number of steps for that one? Okay. So we're just going to do P1. I'm going to do, right now, let's call this BFS. Panic. Not found. And then we'll have P1 just be on the input. And P2, we want to do BFS, BFS on the input, but first we want to do input.push 0 0 twice. Oh, it's on input dot equipment because they're both on the main floor, right? First floor. There's one for each of the things. I mean, I can just, oh, you know what I can do? What? Input equals input dot. What was it doing? What the heck? Did I break it? I solved part 1, right? $47 seconds to do 57. That is the right answer. Woohoo! Okay, so that can't be the fastest way. Right? Like that for part 2, 47 seconds to answer it. No bueno. So why is it 47 seconds? Did we really just sit and stare and watch it for 47 seconds too? I'm sorry, I'm out of it. That's kind of funny. Probably not to the people watching this, looking at me stare at my screen. Yeah, so this is the problem, is like it becomes explosive when you like add 2 more items, right? So it only took 57 steps to get there, but it took 47 seconds. So do we try A star? Like the distance thing is probably pretty close. So we could do fn dist self bool self dot Iter.map chip generator, and it's just their distance from 3. So like 3 minus, I guess it'd be 6 minus chip minus generator summit. That's not a bool. That is a U size, right? So we have some distance now that we can do our A star with. And we just prefer that. I mean, what my inclination to do is, because what we actually want to do is change the frontier from being a vec deck now to a min heap with a sortable thing. So let's look at that. What do I want to look for? Rust binary heap. Yeah, I want to do my own type on it. So it's just a binary heap. It needs to impl ord. So we impl ord or state. Ord or state. Which ones do I have to implement? I think it's just comp, right? Yeah, and it does the other ones. Okay. So, I actually want to do it for a node, I think, because I want to do the cost as well. So we'll have a type node struct node, and it's going to have a state, and it's going to have a cost, and it's going to have a dist. So we first want to comp by cost, lowest cost. Well, we actually want to do order by cost plus dist. So it's like self.cost plus self.dist .comp other.cost plus other.dist. I actually think I need to do it the other way. Oh, you know what? Could I use what doesn't it like? Oh, I'm supposed to enter. I'm supposed to do partial ord. What's going on here? Chat GPT. This is just me not knowing about Rust, I think. How would I implement my own type for a min heap? Debug clone impl ord min heap. I want to use binary heap. How can I make my struct compatible with it? Is actually what I'm asking. This one's going long, sorry guys. My type doesn't impl ord or partial ord. No, it is just ord. And you, oh, equal, partial, equal. Okay, equal, partial, equal. Okay, it's still not happy, I presume. Oh, I need to impl both. Okay, this is kind of starting to make sense now. I think this is what partial comp. Okay, now node does this. Oh, do you know what? I should have just done the pathfinding, right? That's silly. Okay. Can I still do that? Well, let's see if this actually helps because I'm basically there. So I have a node. I have a partial ord for the two nodes. Oh, but I want to do min, so I want to do reverse of this. Right? Yeah, I think I want to do like other self like that. And then the frontier is now going to be a binary heap of node. The state is this, the cost is 0, and the dist is input.dist. Like that. I just pop now. While let some node state cost dist. Can you do something like this? Oops. Sorry, count. Did I do count? Actually, I like cost better. So we do cost dist, but we don't actually use dist. Okay. Node state is this cost plus 1 dist equals successor dot dist knows. What doesn't like about this? Oh, insert. No. Just push. Okay. Push. Does that do it? Doesn't feel like it's any faster. I see. I don't think the A star is actually going to work. What else could I be missing? I don't think the A star helps. Like, I think this is A star, right? Because presumably the lower distances, the things that are like closer, this could potentially make it worse. Is like, you know, the thing that I'm worried about. Because it just has to search longer. What else? Is there some trick to prune? Let's just make sure. My dist. Okay, I get the same answer and it takes about as long. My dist is 6. Minus where the chip is. Minus the thing. So if they're all on worth, the dist is 0. Which is good. We want... You want your, like... For your A star, you have like your heuristic, and you want it to be like, how far are you away from the goal? But it may just not be having an effect, a big enough effect on this thing. Okay. I mean, we can try and, let's see. Should we try and look for other solutions? Advent of code 2016 day 11. Is there anything else that I'm missing before I do this? I am pruning visited states. Sorry, I guess I should look at these, see what they're saying. The basic idea here is a BFS, got it. But you have to prune all racing states, otherwise your space explodes. There are a couple of important extra. They're all individually spoilered here for my estimation of importance. Feel free to look at each one individually. Minor, if floor 0 is empty and you're on floor 1, don't move down. Okay. Kind of important. If you can move 2 items upstairs, don't bother bringing 1 item upstairs. If you can move 1 item downstairs, don't bother bringing 2 down. Okay. Let's say I'm on a floor with hydrogen and chip. So the generator and chip. And let's say that I've decided that my next move will be to move 1 of the 2 chips up the floor. Doesn't matter which chip I move. Uh-oh. Oh, that's true. They're essentially the same. Okay, so I need to do better pruning. Is what this is saying to get to a faster optimization. All pairs are interchangeable. Like what that's saying is if L1, L2 or if the lithium ones are on different floors, that's the same as the hydrogen ones being on different floors. Okay. Yeah, okay, that is an important like one, right? Is we are okay, I want to get rid of this stuff. I don't think the A star works. It doesn't matter. Okay. So how do I create like a hashing function for this thing? Like if they're the same. Oh, is the hash if I just sort them and then they're the same? Can I impl hash for this? Self.write usize. Self.elevator. And then I want to let mute equipment. Like I don't know how to write how to impl my own hasher. I'm trying to think like how do I impl this? Oh, I guess I'd probably just go e equipment.iter dot for each I'll get there. Sorry, it's late. No, chip generator state.write usize chip. Then do the same thing for generator. Then I don't need to do this. I don't know if this helps either. Doesn't feel it. Actually feels like it's making it worse. And can you hear my computer whirring? Or is it going to crash? It makes it worse. So that must not be doing what I think it's doing. My thinking is like for each of the equipment locations, if I sort them, they would be the same. Isn't that what this is saying? Right here. And we can look at his code. Hmm. This one looks like it's math. Oh, it doesn't work for all starting states. I calculated by hand in about 10 minutes. Took him 6 hours. We're not there yet. Well, technically we have the answer. It's just really slow. I mean, maybe I leave it at that and work. I'm going to try for a few more minutes. Do move, find path. Check valid. Okay. A star search. See, it's not clear to me that the A star helps. Did I do it wrong? Oh, this is a cool way to do it in Python. Yeah, I think he does it the same way as me. The priority is the new cost minus. Oh, he's tweaking the heuristic. So, It's however many are on the third floor times 10. Okay, so I wasn't meant to be doing this for 2 hours. Priority is the new cost. Cost so far. Next plus new cost. Okay, so there's like some combinations of costs. I mean, I'm still not convinced the A star works. No code. Yeah, part 2. Ashamed of this code. Ran in 6 minutes. Yeah, why wouldn't my... hash set. Hash or equality. Okay, so do I need to implement equality too? Is that it? Maybe I don't impl equal, or I, you know. Can I implement equal? I guess maybe it's partial equal. Self dot elevator equals other dot elevator, and then self dot, or wait, we gotta do let se equals equipment dot clone and OE equals other dot equipment dot clone. This is, I'm just learning a lot of silly stuff about Rust that hopefully to help me optimize this. Whoa, that is a lot faster. Okay, so what was I missing? I wasn't paying attention to what fx hash set does. So if I just impl equal or and partial equal, do I need to do this? No, it appears that I need to do both. What if I do hash like this and do this? Nope. Okay. That is definitely something I missed. What should I have done? Part of it is I'm just tired. I can't just blame it on that, though. I don't know if I would have gotten to this key thing right here. And what is this saying? Is essentially saying, you know, if you ever have something on, if, like, let's say you have the helium on 0 and 1, and you have the lithium on 0 and 1 as well, you know, how do I say this? If in one state you have helium on 0 and 1, that's the same as another state where you have, where everything is equal, plus you have helium on 0 and 1. Am I explaining that right? Essentially, it's saying like, well, what I did was I said, oh, if they're, if I sort this vector, that means that they're in the same spot, or that, and it's the same, then that means the state is equal. The idea being, like, if I've moved two of them up in one state, and then I go back to my previous state and I move some other two up that are like the same, like chip and generator, that's like the same state, so there's no reason for me to do that one again. Okay. So in the future, how do I resolve that? I mean, the fact that it's taking 47 seconds is definitely bad. If I'm competitive programming, I probably just try and solve. But if I'm, you know, trying to find some fast solution that's like in the spirit of the game, I should probably consider the states deeper, right? Like, that's what it's taking long enough. I knew the only solution was a BFS. I even tried A star. Maybe I did the A star wrong. I don't think so. Well, it's possible that I didn't give enough weight to the heuristic. Like presumably the closer you are to the end, the less you have to do it, and then the closer you are to a solution. And so that should have had more weight. So I should have like taken that value times by 10 and then subtracted it from like 100 or something like that. Something along those lines to say like the further you are away, the worse it looks. And so you skip that for multiple levels. I don't know. Okay. I've spent way too much time on this. This is one where I'll definitely just go through and refine it. But I think the thing to learn from it for me is, yeah, if it's taking time and you're sure that you have the solution, namely BFS, you're sure you have the right algorithm, look for optimizations in the state space of the BFS. And in this case, it's this that solves it. Okay. Yeah, that was a long one, people. What was the timelines? Let me just look really quick. So we got to solving by 7 minutes, and it took us a whole hour just to do part 1. Yikes. So part 1 was doing all this stuff. I probably need to type faster and think faster is what that means. Part 2 I solved in 3 minutes. I guess I can show you this. So I did my intro. Part 1 or reading it took 7 minutes, which is long. Presumably if I'm doing it competitive, the read the problem statement happens in like, a few seconds to 30 seconds. Part 1 took an hour. So that was the parsing, which is this code right here. Sometimes I feel like the functional thing helps, and sometimes I feel like it hurts. So that's a possible thing to think about, is like, is this going to be too much effort to do the functional part of it? And maybe I don't focus on that. But part 1 took that, and then these functions. The valid wasn't too bad. The successors was hard, I feel like. But it still took me an hour to do. Okay. So I got to speed that up. And then part 2, it just took 3 minutes, and it was literally just me adding this and then waiting for a minute for it to finish. And then, yeah, we spent 43 minutes trying to refine it. So what was the refinement part of it in the conclusion was trying an A star, failing at it, going and looking for help, and then figuring out how to do these functions. Okay. Okay. Well, let me know what you think. If you're still here, I don't know how you're here. It's amazing. Thank you very much if you're still here. How did you do it? Did you find the little tweaks, or were you like that other person we read where they said they spent, what was it, six hours? I wonder what the 6 hours is. I mean, it takes time, right? I say that why it takes 6 hours, but here we are 2 hours into this video, so LOL, who's laughing at me now type thing. I guess technically I'd solved it by 78 minutes, so it took me a little over an hour. It may be that Rust is slow too. So there's things you don't have to do. I was just thinking, could we look up the leaderboard? Leaderboard, day 11. 8 minutes. Let's see. I solved it in 78. So that's an hour and 15. It's not an okay. I actually placed then. Technically, I'm like right here in this range. So I actually get top 50. It is way more competitive though. And some days are obviously, yeah. Oh, see, some of these still take, this one's 7 minutes. Presumably some of these days, I don't remember which days were super easy. 6. What was day 6? That one was easy, but it still took me like 20 minutes, right? I think I was like in the 20-minute range. So I don't think I get it on that day. Probably not. So anyway, there you go. Just some food for thought. Maybe I can, it's definitely more competitive, right? Like 2024. Like, I don't know. You pick a random day leaderboard. Oh, yeah, some of these are being solved in seconds. Like 5 minutes if you don't solve it in 5. One of the problems though is you do have AI ones in here. This one was a little harder. 12 minutes. 17. Okay, this one was harder. 44 minutes. You still get in the top 100. Anyway, food for thought. I'd love to hear your thoughts on today if you're still here. Bye, everybody.